I'll start with just a recap of the last lecture about the Euclidean algorithm. Any particular questions on your minds about it? No? Okay. Steve, you won't see me again today. Stephen's going to take my analytical methods lecture to make up for last week's. So
1 hour only.
Okay. So last time we looked at the Euclidean algorithm. We looked at it mainly by looking at a few examples. That's the best way to meet it first time. And we should understand it's a very good algorithm. It's a fast algorithm in the range of kind of number theory type algorithms, I guess. You can deal with extremely large inputs and give the answer quickly compared to the sizes of those inputs, really. So what it does is you give it a pair of integers, a and b, and it returns two things. It returns, firstly, primarily the greatest common divisor of the two numbers. Okay. This is the largest positive integer that divides both of them. And secondly, it also returns the pair of coefficients, m and n, which when you form this linear combination actually equals the GCD. So it gives you the value of the GCD and then the two coefficients. So A and B are the inputs, and the way it works is, we've got a formal description of it here, is you start performing integer divisions. So you begin by taking A and doing an integer division of it by B. It goes in a certain amount of times, Q1, could be a positive or negative integer. And then you get a small remainder. You get a remainder R1, first remainder. And the remainders we ask to be, so we do the integer division and we insist that the remainders are non-negative, and strictly less than the number B you put in. Okay, we're assuming here that both numbers are positive, just so we don't have modular signs all over the place. Okay, we're assuming both of the inputs are positive. So I was about to insert absolute value around B, but it's not needed. So that's your first integer division, and of course, remember the previous lemma 2.4. Lemma 2.4 assures us that the GCD of the pair A and B is equal to the GCD of the pair B and R1. Okay? Whenever you have an integer division with a remainder like this, the greatest common divisor of the initial pair is the same as the greatest common divisor of the second element of the first pair and this new remainder. Okay? So that means you then focus on B and R1. And that's a simpler problem in a sense because the R1 is smaller than B. So your new pair has got a smaller size than the previous pair, A and B. So you just do the same thing again. You perform an integer division of B with R1, and that produces a remainder R2, which crucially is smaller than the previous remainder R1. So that second equation then would tell you that the GCD of B and R1 is equal to the GCD of R1 and R2. So then you focus on R1 and R2, divide R1 by R2, get a remainder of 3. Okay, so you keep on shunting off the first element of the pair and bringing in the new remainder that you produced. That gives your new pair, and you keep repeating the process. So what's going to happen here, see, at every stage we insist that the remainders are positive and strictly less than the previous one. So the process has to end where, if you like, this can't be done with a remainder that's strictly positive because we've reached divisibility, where the first element of the pair is divisible in the sense that we defined it a few lectures ago, is divisible by Rn, and it just goes in cleanly as an integer multiple of Rn, and there is a remainder if you like, but the remainder is 0. Okay. And so these equations continue going down, and then finally you get that the GCD of whatever it was, Rn minus 1 and Rn, n is now going to be the GCD of Rn and 0. And the point we made last time is that you don't need an algorithm to tell you what the greatest common divisor of something 0 is. It's just automatically does what the other number is, okay? Because everything divides 0. Everything divides 0, so the biggest thing that could possibly divide these two would just be r. Okay? Bigger number can't divide a smaller number. So it's just easy answer. This is obviously Rn, but then Rn is then the GCD we were searching for all along, okay? The GCD of the initial pair, A and B, okay? Because from each of these integer divisions, each one generates an equation between GCDs which links them all together, okay? GCD BR1, GCD BR1, GCD R1, R2, that'll be the one on the left in the next equation. So that's a nice process. It's an algorithm because it's perfectly clear what to do at each stage. There's no ambiguity or anything. And it certainly finishes in a finite amount of steps because you've got this sequence of remainders which are non-negative and getting smaller. So they have to crash into 0 eventually. Okay? So once we set off the computer calculating it, we know for sure it's going to stop. And providing you're still alive when the computer stops, we can read off the answer. All right. Okay. So any questions just about that first part? So we looked at that last week. We looked at several examples, a few examples. It's a nice example at the top of the page of it working. So you start off with this, unmanageably large pair. There's no intuition about what the GCD might be between those two. We keep doing integer divisions with remainder. An integer division with remainder is quite a quick operation for the computer. There's no itself. Okay? There's no ambiguity about it. So you get this chain of relations between the GCDs, and then finally, at the end, GCD of 6 and 0. So obviously the answer is 6. But then the second thing the algorithm gives us is these two coefficients, the m and the n. So it constructs the linear combination between a and b that's equal to the GCD. And the way it does this is by working backwards through the sequence of integer divisions you've just produced. Well, 0 is 0. We don't need a linear combination with 0. But if you look at the second last equation, you've got Rn, which is the GCD. This thing is the GCD of AB. The second last equation gives you Rn as a linear combination of Rn minus 2 and Rn minus 1. So that's good. That's part of the way towards a linear combination of A and B. Then the equation before this one, the equation just before this one will have Rn minus 1 as the remainder. And so that equation on its own will provide you a linear combination for Rn minus 1 as a linear combination of Rn minus 2 and Rn minus 3. So you use that to substitute in for this Rn minus 1 in this first linear combination. So then you have a linear combination for the GCD as a linear combination of Rn minus 2 and Rn minus 3. Okay. Further up the chain of remainders. Okay. So you keep using each equation to get rid of one of the remainders and give you the linear combination, the linear combination for the greatest common divisor as a linear combination of an earlier pair of remainders. Okay. So you work all the way up. Eventually you'll have, just before it ends, you'll have the GCD as a linear combination of R1 and R1 and R1 and B from here, once you eliminate the R2. And then the very first equation replaces R1 as a linear combination of A and B. Once you make that substitution, then you'll have GCD as a linear combination of A and B. And you'll have identified what the values of the coefficients m and n are. Okay? You can see that working in the previous example here. So this second last equation here, 6, this gives 6 as 24 minus 18. And the previous equation gives you 18 as a linear combination of 138 and 24. So you substitute that in and collect together terms. So you don't evaluate any of these products or anything. You just evaluate the terms. You've got some 24s here, some 24s here, 6 24s and minus 138. Then the previous, the the equation before that will allow you to get rid of 24. You use that to substitute for 24. Now you've got the GCD as a linear combination of 162 and 138. So we're moving up the chain of, moving backwards up the chain of equations and getting a linear combination for 6 until eventually we make the last substitution and we get rid of the 162 and we're left with 6 as a linear combination of 1, 2, 3, 7, 8 and 3, 0, 5, 4, which were the initial pair that we were provided with. So we've calculated there the 132 and the negative 535. They're the two linear combinations. Okay, now there's a bunch of exercises there that ask you to do examples of these. So please do work through those in the meantime, and we can really look at it on Fridays, on tutorials on Fridays, see if there's any remaining issues with it. But any questions about that at the moment? Is everybody happy enough with the equating algorithm? Okay. It's a really nice algorithm, and it's really nice. Yeah. And it runs really fast, and you program it up. Even if you program it up in something as simple as Python or a little function you write in MATLAB, it's still extremely fast. You can give it ginormous integer inputs, and it spits out the answer really fast. Okay. Using the inbuilt version, there are already a GCD function in MATLAB or in Sage and that. Using those will be even faster because they're compiled code and they do their operations with proper, binary representations of integer rather than doing the integer operations in the higher level of the package, MATLAB or Sage. But they are lightning fast, those properly software engineered implementations. Okay, so we have that. So it'll be a practical use in the cryptography part, because it also gives you. It allows you to obtain modular multiplicative inverses of numbers. John talked to you yet about modular multiplicative inverses for some of the cryptography stuff? No? A little bit, yeah. Well, they'll be very important in cryptography, and we'll be dealing with those things. We'll be dealing with them formally in the number theory part as well. So we'll be referring back to the algorithm as a useful tool in the future as well. Okay, then, so we're going to finish out this chapter 2 then. There's a couple of results here which it talks about on page 14. And we want to make a few references to the least common multiple. It's a kind of partner quantity to the greatest common divisor. And then we should get a start on chapter 3 before 10 o'clock. And we'll see a really nice result from chapter 3. Okay, so we've got another result, which is a theorem about the GCD. And the proof of it that's here in the notes is using the concept of the Euclidean algorithm. But I can also give another type of proof to it, but we'll have a look at both of them. So if m is a positive integer, so this is really a nice kind of factorization result about the GCD. Greatest common divisor of a pair of integers. If there is a common divisor, m, in the pair of inputs that you're giving to the GCD, it'd be nice if there was some kind of factorization result that allowed you to take out the m, so to speak, cancel the m. And naively, just looking at it at a structural thing and how might it behave, you maybe might expect m to come out, or m squared, maybe, perhaps, because there's two m's there, so maybe it should come out as m squared. But of course, when you think into the definition of what it actually is, greatest common divisor, we see that the correct way it behaves is that one m comes out. Okay? So you can cancel the m from both of the inputs, and that m then multiplies the GCD of the smaller pair. So the proof of this idea presented in the note, so this is really nice, it allows you to simplify the arguments to the GCD function. The proof in the notes basically works that if you think about how the Euclidean algorithm is operating with A and B. Well, the first equation produced is an equation like this, where the remainder R1 is, assuming we don't have perfect divisibility, let's say the remainder R1 is greater than or equal to 0 and strictly less than B. That's what the first equation looks like. Sorry, no, plus O. That's what the first equation looks like in the Euclidean algorithm. But of course, this is exactly equivalent to, this kind of equation and inequality are only true if this one is true, where we just simply multiply the whole equation across you multiply both sides of the equation by m, you multiply both sides of the inequality by m. In fact, m is a positive number, there's no flipping of the directions of the inequality. So, that first integer division with remainder is exactly equivalent to this one. Okay? And it's this one which operates, this is the one which begins the Euclidean algorithm for the GCD of MA and MB. So, but if all of the integer divisions are just going to exactly mirror the ones for GCD of A and B, except that everything has got an m in front of it, then it's going to end in the same way, and the GCD of MA and MB will be simply m times the last non-zero remainder that we got when we ran the Euclidean algorithm for A. Okay. So I think that's summarized in the notes there, but the Euclidean algorithm for MA and MB is simply the same sequence of equations, as appears in the Euclidean algorithm for the pair A, except they're all multiplied across by m. So the Euclidean algorithm for MA and B is simply the same sequence of equations as appear in the Euclidean algorithm for AB, but multiplied across by n, so to speak. So the thing that you end up with at the end, the output for GCD AB will be this number D, and the output for GCD MA MB is going to be this number D multiplied by n. Sorry, the handwriting. The Euclidean algorithm for MA and B is simply the same sequence of equations as appears in the Euclidean algorithm for AB, but multiplied across by n. I'll try and write better. So that's theorem 2.5. You can also prove it without reference to the running of the algorithm, by simply noting that, let's suppose D equals the GCD of AB, then, part of the definition of the GCD is that it is a common divisor. Okay, it's the greatest common divisor, but it's certainly a common divisor. Well, that will imply that MD divides MA and MD divides MB. That's one of the properties of this property of divisibility, that if you've got x dividing y, then mx divides my. That's one of the parts of theorem 2.1, which was our list of basic properties of divisibility. Or maybe it isn't. It's one of the exercises. Well, it's not, it should be. No, it is. Sorry, it's this part 7, the last part. A divides B, you can only obey C divides B. Yeah. Okay. So that says so MD is a common divisor. A common divisor of MA and MB. We're trying to prove it's the greatest common divisor. How do we prove it's the greatest common divisor? How do we prove it's the longest number, the largest number that divides MA and MB? Well, we can do that if we can show that every other common divisor must divide MD. Okay. So we'd like to have some way of knowing that any other number that's a common divisor of MA and MB is also a divisor of MD. So we know that there exist integers alpha and beta giving you a Bezoos identity for D as a combination of A and B. Okay, that's Bezoos identity. So that GCD of a pair of numbers can always be realized as a linear combination with integer coefficients. But of course, that immediately we can multiply across by M. And what we have now is a linear combination of MA and MB, giving us the value MD. Okay. So if C is any other common divisor, C divides MA and C divides MB, then C must divide MD. And that's true by theorem. There we're using the divisibility of linear combinations, so that's true by theorem 2.1, part 3. And the fact that if some number C divides an X and a Y, then it also divides any linear combination. So here's C dividing MA and C dividing MB, but we already have MD as a linear combination of MA and MB. So therefore the C must divide MD. So MD, D remembers the GCD of AB. MD is a common divisor of MA and MB, and every other common divisor divides it. Divides MD. So therefore, MD is the greatest common divisor. So that's a nice little result about the behavior of GCD. There's a common divisor in the input, so you can cancel it, and it multiplies the GCD of the remaining 2. And so that's nice to know. There's 2 proofs there. One, thinking about how the Euclidean algorithm would run on the inputs AB and the inputs MA and MB, it would run essentially the same way, but multiplied by M. Or alternatively, we can, again, just argue directly from the definitions of divisibility in GCD. And again, crucially, this crucial idea of Bezoos identity appearing, arguing based on linear combinations. Seeing that GCD is a linear combination. It's a very common step in any kind of argument surrounding divisibility or prime inverses. Okay, so if you're ever stuck in the middle of a problem, always think, and it's to do with divisibility or primes or factoring, always thinking about, well, can I use the concept of linear combinations anywhere here? The fact that something is a linear combination of 2 other things can often come in handy. Okay. So before we leave the GCD, it kind of has a partner. There is a partner to GCD, which is the LCM, the least common multiple. So just as you can have the greatest common divisor of a pair of numbers, which is the largest number that divides into them both, so you can, we might also look at the least common multiple, which is the smallest number which is simultaneously a multiple of two integers. Okay? So this is defined in 2.6, definition 2.6. The LCM of AB is equal to basically the least common multiple of A and B. Its name is its definition. Okay. When I say partner to GCD, it really is an equivalent construct in that it's directly linked to the GCD in the following way, in the way which is made clear in theorem 2.6. Oh, we should give some examples. So what's a nice example? 6 and 4 is
6.
LCM.
Oh, sorry, yeah. 12.
12, good. You redeemed yourself. The GCD is 2. GCD is 2. The least common multiple, the smallest number that is simultaneously a multiple of 6 and a multiple of 12. So, okay, and the fact that the GCD is 2, 2 times 12, which is, of course, 24, happens to be equal to the product of 6 and 4, which was the original pair we were looking at, okay? And that's no coincidence. So theorem 2.6 proves this in general, that the GCD of A and B, if we multiply it by the least common multiple of A and B, we will always get the plain old product of A. So this shows us that GCD and LCM are inextricably linked. You know, if you know the value of GCD AB, you automatically know the value of the least common multiple because it's equal to the product divided by the GCD. And vice versa. If you know the LCM, therefore you automatically know the GCD because the GCD is just the product divided by the LCM. Okay. Now we can notice that in examples. We can probably start to get an intuition about it for small pairs and so on. But, you know, the fact that it's true in general, you know, we should only really believe that once we've seen the proof of it. So how does this proof work? I'll sketch out the main ideas on the page, but the kind of fully commented versions in the notes. Yeah, so if we're going to let D equal, just to save us writing GCD of AB all the time, just write C for the greatest common divisor. We will, so the way the proof works is we will prove that the integer AB divided by D is the LCM of AB. And that will prove the result. Now don't just say, well, of course it is because you divide both sides by GCD and there it is. Yeah, but we're trying to prove this equation. We haven't proved it yet, so we can't use the equation to prove this. Okay. So we name the GCD of AB as D. We will prove that this number, which looks like a fraction, but crucially is, we know it's not a fraction because D divides A and it also divides B. So A divided by D will give you an integer answer, and that will be multiplied by B. So that thing, it looks like a fraction, but it is an integer. We'll show that this is the least common multiple of AB. Now, we will need to access the complementary divisors of D as it divides A and B. Right, so D is the greatest common divisor of A and B, so it's certainly a common divisor. So you can write, sorry, that's nonsense. A is alpha D, B is beta D. D is the greatest common. Excuse me. the greatest common divisor of A and B. So we can write A as a multiple of D, B as a multiple of D. It's convenient to name them alpha and beta. This keeps the association with A and B. So then if we consider the quantity AB divided by D, on the one hand, we can see this as alpha dB over D, which is therefore alpha B. Cancel the D's, but also we can instead cancel the D out of the thank you. B to D. Too many things floating around. So replace the B by B to D, and then we can cancel that D there. So this is, so that's also AB over D equals this, which this equals beta times A. So what we've seen there, why are we doing that? Now this same quantity, AB over D, it's simultaneously a multiple of B and A. So that shows it's A common multiple. So AB over D is a common multiple. So that shows, we've shown it's a multiple of B and a multiple of A. Alpha and beta are integers, of course. But we need to show it's the least common multiple. So we have to imagine any other common multiple. So consider any other common multiple. Let's say C, which is equal to, what have I called it, a lambda times A and a mu times B. So there's some other number C, which is a multiple of A and a multiple of B. We will now show, that AB over D divides C. Remember, that looks like a fraction. It's not. It's an integer. So we will show that AB over D divides C. So in other words, AB over D is less than C. Okay. We know AB over D is a common multiple. The fact that it divides every other common multiple, that will show that it's the least common multiple. Okay. This will show that AB over D is the LCM. The LCM figure. Now, how do we do that? Well, we do it again. Just illustrate the point yet again I was making. We do it with the aid of the Bezout's identity. So we can express D. Remember, D is the greatest common divisor of A and B. Just a reminder, we can express D as D is MA plus NB, where M and N are integers. And what we're going to do is consider the quantity C divided by AB over D. Remember, we just declared we're trying to show that AB over D divides C. So we're going to divide it. We're going to divide C by AB over D and demonstrate that the result is an integer. Okay? Because if we can show that C divided by the thing in brackets is an integer, that means the thing in brackets divides C. Now, just to tidy this up as a fraction, this is, of course, DC over AB. We can use the linear combination for D to suddenly replace B with MA plus NB over AB. And multiplying that fraction out will give CMA over AB plus CNB over AB. CNB is the Country Music Association of America, I believe. CNBs. Can't think about CNBs. Anyway, out of this fraction, you can cancel the A's. And out of this fraction, you can cancel the B's. And then we remember that C isn't any old number. C is a special number. It's just there at the top of the screen. C is a common multiple of A and B. So the fact that it's being divided by C by B there, in the first fraction, C divided by B, it's just going to be equal to mu times M. And here we've got C divided by A. Well, that's just lambda times A. And the point about getting to this stage here is now I can declare that this is clearly an integer, okay? Because it's just a product and a sum of integers, okay? That's the point here. That's the conclusion there. That's why I wanted to do that. See, I would struggle to have said before exactly why DC over AB. I mean, it looks like a fraction. It's not immediately obvious that it isn't, that it is an integer. So I had to show clearly that this quantity was an integer. And I can say that down here, because it's just a combination of integers. So that shows that AB over D does divide C, and hence, as we've already argued or already set out, AB over D is the least common multiple of A. Okay. So that establishes that nice equation in theorem 2.6. That the product of the GCD and the LCM is just the plain old product of the two numbers. Again, notice, appreciate the use of Bezo's identity coming here again. It's remarkable the number of times it occurs in these arguments. If you look through the whole book and count the number of times we make use of this fact that the GCD is a linear combination of two numbers, it happens all over the place. Okay. So, as I say, please work through all these exercises in chapter 2. There's a whole bunch of them there. And we'll have a good look at those on Friday in your tutorial. And I'll release the solutions to them all then after Friday, after the tutorial. But, so there's plenty of ammunition there to be dealing with. So that's going to bring us on to chapter 3 then. And we've only got 10 minutes left this morning, but I would just like to have a look at the beginning of chapter 3. And if you haven't seen it before, hopefully send you away smiling and in a good mathematical mood this Monday morning, because we'll see one of, arguably the most famous results in maybe mathematics, but certainly in beginning number theory. This is the real thing. It's just something everybody should know about, really. Okay, so I think everything in this first page we've already covered. I've already done this induction proof. Okay, so a prime number is a positive number bigger than 1, which has no divisors apart from itself and 1. Everything is divisible by itself and 1. Okay. Composite numbers have extra structure. They divisible by other interesting things, midway between themselves and 1. But prime numbers are special. They have no other divisors apart from themselves and 1. And yourself and 1 isn't interesting divisors. So essentially, prime numbers have no divisors except themselves. 2, 3, 5, 7, 11, and dot, 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 dot. So that's the thing we're going to settle in a few minutes. Theorem 3.1, we've already proved. I proved it to you as an example of strong induction. Every integer factorizes into a product of primes. It essentially just comes straight away from the definition of a prime number. If a number is not prime, therefore it factorizes into smaller numbers, and you keep examining these numbers. Are these numbers prime? If they are, fine. If they aren't, factorize them. You keep factoring everything as much as you can until eventually you're left with a product of primes for the original number. Okay, so every number factorizes into a product of primes. The crucial thing is, and it has grand standing name, the fundamental theorem of arithmetic. The crucial thing is that the way an integer factorizes into primes is unique, meaning there's essentially only one way to factorize a particular integer. So the uniqueness part is something we have yet to prove, and then we'll prove that in the next lecture. But what we want to prove for the moment is settle this thing. So we've written dot, dot, dot there, so that suggests the primes continue. Indeed they do, there's lots of them. We found some, you can look up tables, we know all the prime numbers up to a certain limit, and then after that our knowledge becomes patchy. We know some sporadic primes, going on into ginormous numbers, but there's huge gaps. There's loads of primes we've skipped over in the ones we've come to record. Because some numbers are easier to test for primality than others. But what we can do is look at Euclid's argument that there's an infinite number of prime numbers. So number theory is characterized by these great results that tell us a lot about things, like a lot about integers in some senses, and a lot about prime numbers. We know an incredible amount about prime numbers. But there's also huge problems, things we don't know about prime numbers. But one of the things we do know is that there are infinitely many. I'm kind of hoping you've seen this already. Hands up who's seen the proof of this already? A few people? Okay, so most of you haven't. Some people didn't. Okay, well, that's great. So, this is when you become real mathematicians, when you know this proof. It's a good proof to know. It's a part, if somebody asks you what you're studying in university, you can sit them down, grab their attention, and lay out this proof to them. If they have any, they should be able to follow you. If they're not frightened to the socks of mathematics or numbers, they should be willing to get engaged. But, so, yeah, okay, this is great. So, I've only got 4 minutes, but it can be done in 4 minutes, okay? So it's a proof by contradiction. So we suppose, on the contrary, there are only a finite number. Okay, we know there's at least 2 or 4 of them, 2, 3, or 4 of them. But let's suppose that this list is exhaustive. This is all the primes. Right? And there's only a finite number then, so they're indexed by the counting numbers. It goes up to some upper limit. We know about millions and millions of them if you look up in the computer databases. So there's certainly a large number. But supposing there was only a finite number, then what we do is we consider the large number that you get, I called it M. So you consider this number M, and this number M is very simply constructed out of these prime numbers. We multiply them all together. You multiply all the prime numbers together and you add 1 to the result. Okay, M is probably pretty big. We know about millions and millions of prime numbers that have been listed by computer search. So you multiply them together, you've got some ginormous number, and you add 1 to it. But it's just a plain old integer. And we've already proved that every number factorizes into a product of primes. So there exists a prime factor. Now what are we going to call it? Well, you see, we've made this assumption that there's only a finite number of primes. So these are all the primes. So let's say it's pi. It must be one of these numbers here, because that's the assumption we've made. So we've got this number pi. So pi divides m. But we can write 1 as a linear combination of m and the product of all the primes. And you see somewhere in there is the prime number pi. And we've just proved that pi divides m. So theorem 2.1.3 should be ingrained in your mind at this point. Theorem 2.1.3 is the divisibility of linear combinations. If we have a number here, pi, that divides two numbers, it automatically divides every linear combination. Therefore, it divides the difference. The difference is a very simple linear combination. So that implies, because pi divides this number, pi divides the product of primes, pi divides m. Sorry, divides 1. Now, what do you think of that? A prime number that divides 1. Is that okay? Definition 3.1. What is a prime? A prime is strictly bigger than 1. The first part of its definition. These are the first few, 2, 3, 5, 7. Here, we seem to have found a prime number that is dividing 1. i.e. pi has got smaller value than, no, it's less than or equal to 1. It's just, whichever way you look at it, it's a contradiction. So this is a contradiction. So it's either the end of reality as we conceive it, because things are true and false. Okay, it's not that bad because we made a mistake along the way, of course. Our mistake appeared at the very beginning, where we supposed that there was a finite number. Okay. So that assumption is the problem. You can't assume that. You can't assume that. So there is not a finite number. There must be an infinite number. And then this argument doesn't work, because you can't multiply together an infinite number of numbers and get an integer. So this argument is nonsense. So there are an infinite number. So it's a beautiful, not the my version of it, it's a beautiful illustration of proof by contradiction, where you assume the thing you're trying to prove is false. You argue rigorously, mathematically, consistently from that assumption until you reach something which is patently outrageous. It's outrageous that a prime number could divide 1. We just know it can't be. So the problem we made was in that original assumption. Therefore, there's an infinite number of prime numbers. So we know that about the primes.